everyone, and welcome to another video. So today I'd like to have a quick discussion on bit manipulation and masking. So this could be a pretty low-level computer science discussion talking about a single bit or a collection of bits, and how does a computer typically deal with operations directly manipulating those ones or zeros. So the lowest level typical operations that you'll see on these bits are sometimes referred to as bitwise operations, and here's a collection of pretty much the 6 lowest level operations that a computer is going to do with a bit or a collection of bits. So it's an and, or, exclusive, or, a not, a left shift and a right shift operation. So let's go through what all of these mean individually. So these top 4 are probably the easiest. You've probably seen most of these, and in fact, this can be a real quick discussion. I think everyone understands what an AND operation is. It's basically if you're given 2 bits, it's either a 0 or a 1, right? So if you have a 0 and a 0 and you do an AND operation, that basically gets you a 0, right? A 1 and a 0 gets you a 0 and a 1 gets you a 0, and finally a 1 and a 1, that's the only one which also returns a 1, right? So again, AND operations, no need to talk about this, we've all seen it. Similarly, an OR operation is really similar. The truth table is here, right? As long as either of those bits or both of them are 1, you'll get a 1 out. The exclusive OR is a little bit less used. We will use it later in this discussion, so I think it's worth talking about. It's really similar to the OR operation, except for the situation when you have a 1 exclusive ORed with another 1. That actually returns a 0, okay? So those are those 3 operations which take 2 bits. Now, how about the NOT operation? Again, this is really simple. This only takes a single bit, and basically if you have a 0 and you take the NOT operation, it just flips the bit. It goes from a 0 to a 1 and vice versa. If you have a 1, it goes to a 0. Okay, so that's these top 4. Let's talk a little bit more about these bottom 2, the left shift and the right shift. So give me a second to erase the board and get a little bit more space. All right, so let's talk a little bit and start with the left shift because that's a little bit easier. So a left shift, this actually needs to work on a collection of bits, not just a single bit. So let's look at a single byte or 8 bits. And let's ask, what happens when you do a left shift on a collection of 8 bits? So a left shift is really pretty simple. All you're doing is you're going to take all of those binary digits, these 8 ones and zeros, you're going to just shift them to the left by however many times you want to shift. So if you're going to do a n left shift, that just means move all these bits n elements or n spaces to the left, and then you're going to end up with some empty spaces on the right. Just pad those with zeros or shift in a whole bunch of zeros, okay? What's interesting about it is if you think about this long enough, each single shift is actually equivalent to multiplying the decimal value of this this number by 2. So every shift is basically multiplying by 2 unless overflow occurs. And we got to be a little careful with the term overflow. Typically overflow usually means when you go over the maximum number of what this this number can contain. But also we're going to see that if you have a signed value, that overflow idea can also happen when the most significant bit changes from a 0 to a 1. And I think the easiest way to see this is with an actual physical example. So let's start with a unsigned case. So let's do something like this. Let's say you have something like this. I'm going to use kind of MATLAB terminology, but basically, or this could be C. All I'm saying is I've got a decimal number 41, and I want to represent that or store that in computer memory as an unsigned integer with 8 bits, okay, and a UN8 data type. Meaning, again, there are 8 bits, so there are 8 slots for ones and zeros, and the way that we are going to interpret these collection of 8 bits is as an unsigned value. So obviously, 0, 0, 0, 0, 0, if all these were zeros, that would be 0. If it was 0, 0, 0, 0, 0, 0, 0, 1, that would be 1, etc., all the way up to, if they were all ones, that would represent positive, what, 255. Okay, because it's an unsigned int, right? Got to be a little bit careful here, and I guess we're going to harp on this because it's going to matter in a second, right? But the U here means unsigned. And I guess this might be another great time to point out that all the lecture notes for this discussion are available. If you go in the description of this video, there's a link to a GitHub page where you can get these lecture notes written out as well as code to follow along with these examples. So that might be easier. Okay, so again, you can execute this line. In fact, we'll jump over to MATLAB in a second and do this just to prove to you that this is true. But okay, let's say you do this, okay? You have a variable x and it's called, it stores the number 41, right? And again, the way it's gonna store that in its 8 bits of memory is as this value, right? 00101001, right? That represents the number 41, correct? Okay, so now what I'm going to do is the next line down, what I want to do down here is I'm going to say, let's do x left shift by 1. Okay, so that just means take these green numbers, shove them over to the left by 1. That's what you see here. I took all of these, shoved them over by 1, and then shift in or pad on the right with a 0. So that's what the red is these padded values, okay? Okay? And you get this value, right? And as you can see, what's interesting about this is if you work out the decimal equivalent to this, you get 82, which is in fact, like we saw, that is just taking x multiplying by 2. That's kind of what it does, right? What a left shift does is it basically multiplies the decimal value by 2. Right? And again, let's do it again. Let's go down here. Let's look at what happens if you went x, shift it by 2 spaces now, right? So again, just take the whole thing, shift it over 1 more slot. So you can see this pattern, it's kind of moving along the diagonal, right? You're just shifting the whole bit over to the left by 1 slot. And again, you get this thing, right? You get 1 0 1 0 0 1 0 0, right? And again, if you take the equivalent of what does this binary value mean in decimal or in base 10, that's 164. And again, we see multiply by 2. Okay, so now though, if we do this one more time, we are going to have our traditional sense of overflow, right? So overflow, what's going to happen here is you can see what happens if we shift 1 more over. This 1 gets shifted out of the most significant bit, right? So again, the most significant bit is up here, right? So this is the most significant bit. And what happens here is we go 1 more time, that gets shifted out on the left. So we sort of lose information because this data type only has 8 bits. So we end up with this number, right? We shift in 3 zeros on the right. We end up with this, and we get, this is actually the number 72. And as you can see, going from here to here, this is not a multiply by 2. So again, we had overflow occur in this case. All right. So again, that's pretty standard. Now, what's fascinating again is let's talk about this last statement right here, where a lot of times you're going to see people say that, okay, this is equivalent to multiplying by 2 unless overflow occurs. And this is typically when I hear overflow, this is what I think of, right? But overflow can also mean if the most significant bit changes from a 0 to a 1 if you have a signed value, okay? So what I mean by that is, what if we changed this? Let's take this to, instead of an unsigned, let's make it a signed int. So again, I got to take this off, or modify this, right? So this now is a signed value, right? It has a sign. And it's going to be used as sign. We're going to represent this using a 2's complement representation of a signed number. And again, if you're not familiar with 2's complement, there are a lot of videos on that. I encourage you to kind of check that out. And again, this is 2's complement. And all that means is that we are going to interpret these numbers a little bit differently. So again, this here, if you execute this, it's still going to store this bit pattern in memory, right? And it's still going to represent 41, okay? But I guess maybe what we can do is we can say this is a positive 41, right? It's the same idea, right? Okay? And then again, we can still shift over by 1. You move this over, you still get this bit pattern, okay? That still represents positive 82, okay? But now, this is where this gets interesting. If we shift this 1 more time, notice that the 1 goes to the most significant bit, right? And we know that in 2's complement representation, the most significant bit is the sign, the SIGN of the number. So if it's a 1, it means the number that's stored in here is actually negative. So what that means is you still get the exact same bit pattern, but we are going to represent it different, or we're going to interpret that differently, right? So in this case, the decimal value of this is actually, it's not 164. This is now negative, what does this turn out to be? Negative 92. So as you can see here, this is not a equivalent of a multiply by 2, right? We actually had another type of, you can call it overflow, I guess. And this is overflow in the sense that the most significant bit flipped from a 0 to a 1, so it breaks this pattern here, right? But again, the left shift, it's still doing the exact same thing, right? It's still just moving all the bits to the left, and then it's just going ahead and padding zeros on the right. So in fact, you can go one more. Again, let's shift one more time. And again, we get this exact same bit pattern. I don't have to touch any of these bits. It's the left shift just does the exact same thing. But again, now notice that the signed bit, right, the most significant bit is now 0. So this is now a positive number. And again, we come back to this is basically just meaning, it means positive 72. So again, that's kind of fascinating, right? So I think the left shift is a good way to start this discussion. Let's talk a little bit now about the right shift equivalent. Okay, so the right shift is very similar, right? What it does is it takes all the binary digits and it shifts it now to the right by n spaces. Now, the only thing that's interesting is now the right shift has a little bit more extra in terms of how are we going to do the padding, okay? So the padding, what happens is if the value is an unsigned integer value, we're going to pad zeros now on the left. But if the value is a signed value, then what we're going to pad on the left is actually a copy of the most significant bit, the original most significant bit. And we're going to see why that matters in a second, okay? What this scheme does is that it means that effectively each shift is now equivalent to basically a dividing by 2 plus a rounding towards infinity. Okay, right? Because you got to take into account cases where the 1 gets shifted out on the right. Okay, so every time you shift to the right, you are basically dividing that number by 2 and rounding towards negative infinity. So keep that in mind, right? It's not rounding towards 0 like most traditional rounding schemes you might do with integer values. But in this case, it's rounding towards negative infinity, okay? So again, I think the easiest way to look at this is with an example. So let's look at an unsigned, right? So again, notice here the U is unsigned. Okay, so we fall into this case. So what we're going to do is we're going to start padding in zeros on the right, okay? So here's the original number. Let's pick something, okay? So it's a 1, 0, 1, 0, 1, 0, 0, 1, okay? And again, since this is unsigned, I don't care that this most significant bit is a 1. This is still a positive number, right? And in fact, it turns into a positive 169, okay? So now, let's go ahead and, again, do the same thing. Let's shift now to the right, this whole thing. So take this whole bit pattern, move it over to the right by 1. Okay, so that's, you can see that it moves over. And then what we're going to pad on this side, in this case, is we're going to pad zeros. Okay, so you end up with this, which is actually 84, which again, as you can see, it's take this number, divide by 2, and round towards negative infinity. That's what we end up with, right? Okay, cool. And then same thing, let's go ahead, shift now by 2. And again, we've just pad now with 2 zeros. And again, we get the nice pattern here. And then finally, X, you can shift this thing by 3. And then we now pad 3 zeros on the left. Right? We're just moving. And you can keep doing this, right? Dot, dot, dot. In fact, in the notes, we'll go over to MATLAB and we'll do this in a second. You'll see that all happens, right? So this is pretty reasonable, right? Now, what's interesting here, okay, is what if we right shift a signed negative value, okay? So let's go ahead and switch this, okay? So what I want to now examine is a different case. Let's look at a signed value. Oops, sorry, there should have been an 8 here because I want an 8-bit data type, okay? Now let's take away the U, okay? So now, and let's change the number here. Actually, wait a second. Yep, let's change this number. UN8 of minus 87, okay? So this is now a signed value, right? It has a sign, okay? And again, we're gonna represent the 2's complement, and I want to represent negative 87. Fascinatingly, what happens, let me get rid of all these paddings because this is where this gets interesting, is how is the padding handled, okay? So let me get rid of these, okay? What's fascinating is I want to start here with Let me erase all these, okay? I want to start with negative 87, okay? Negative 87, okay? And actually, that is this bit pattern, right? It's the exact same bit pattern we were just dealing with, but now if this is a signed value, this bit pattern actually means negative 87, okay? So now we are actually in this case where, all right, I now have a signed value, okay? So now when we pad in on the left, we are going to pad in a copy of the original most significant bit, right? So again, we got to be careful. Here is the original MSB, and it's a 1. Right? So what that means is when we shift this whole thing to the right by 1 space here, I got to pad this with a copy of this. So I'm going to pad this with a 1, okay? And the reason you want to do this is because now with this bit pattern in 2's complement, what this actually is this is actually minus 44. And again, we see that it's the same thing. It is a divide the original number by 2 and round towards negative infinity. Right? And again, you go down here, so shift it again one more time, and again, pad with a copy of the original most significant byte. So you get this. And again, if you plug this into a 2's complement calculator, what this guy comes out to be is negative 22, right? And then you shift this sucker again by 1, and then we're going to pad with copies of the 1s, right? And this comes out to negative 11, and etc. You can keep following this along. So now, this is what's interesting about this, that this is sometimes referred to as like a sticky right shift, because it's gonna stick whatever the most significant bit was and shift it as you're going, right? And it does this to basically handle this reasonableness or this normal logic and interpretation. So this is sometimes what's referred to as an arithmetic shift versus a logical shift, right? So this here is an arithmetic shift, right? Where we're doing this sort of logic here versus what a logical shift would just always be padding with zeros. It's just moving to the left or the right and always padding with zeros. But here's where this nuance comes into play, okay? Now, maybe let's do one more example just to make sure we're all on the same page here. Let me look at a different number. How about, okay, so I've got this all set up. Let's go ahead and do the exact same thing. We're going to use a signed an int8 value. Now let's use the number 19, okay? I want to look at the number 19. So this is what the bit pattern is. It's 0001 0011, right? That's a 19, okay? So now, again, we are still in this situation right here where it is a signed value, right? Basically because we have an int8 here. So when I do the shift, I've got to get a copy of the most significant bit. And again, what we see here is in this case, the most significant bit is a 0. So now when I shift to the right, I need to now pad in a 0 on the left, right? And again, the reason we do this is because now this bit pattern is equivalent to 9. And again, we get the divide by 0, go round towards negative infinity. And again, you shift it again. Now I just pad in 2 zeros. You get that, pad in 3 zeros, you get that, etc., etc., etc. So this all works. So tell you what, let's jump over actually to the computer and just do this in like a program like MATLAB, or just to make sure that these all check out. All right, so I've just got a quick MATLAB script set up to test some of these left and right shifts. Again, feel free to download this off of the GitHub page. So in MATLAB, it is a function called BitShift that will basically do the left and the right shifting. So you basically give it an integer of how many times you want to shift to the left or the right. So left shifts are positive numbers, right shifts are negative numbers. So let's just first do this first section here. So again, this is basically what we did on the board. And we're just going to go and shift by 1, 2, and 3 and see what happens. And I'll just print the results over here. Yep, this is exactly the example we saw on the board, so everything pretty much checks out. Now let's do the same thing we did now with, instead of having an unsigned int like we saw earlier, let's have a signed integer and do the exact same shifting. So again, we see that the bit patterns are exactly the same. So this set of bit patterns here is the exact same as this set of bit patterns, except now the only difference is how that decimal number is interpreted. And as we see, we get the 1 in the most significant bit, which turns into a negative number using 2's complement discussions, right? Okay, so that's the left shift. Let's now look at those several cases of the right shift we saw on the board. So again, let's start with the unsigned value. So here we go. Here's the 169 in decimal, which was this bit pattern. And again, because it was a unsigned value, when we start shifting to the right, we just pad in with zeros on the left no matter what, correct? All right, now let's do the more interesting cases where we're going to right shift a signed data type. And now let's start with a negative number. So let me just go ahead and actually, let me run this next section of code where I just keep shifting. So that's here. You can ignore this. All I'm doing right here is I just wanted to demonstrate how some computer languages, in this case MATLAB, we had a bit pattern up here, this unsigned integer of 8 values, which was, I can't remember where we had it, but anyway, what ended up happening, oh yeah, it was this one right here. It was this bit pattern, right? And I was going to try to cast it to a signed value. And again, what it does is it actually goes ahead and casts it to the maximum positive number. So earlier the decimal value was 169. What this ended up doing was changing it to a positive 127, which is somewhat reasonable, right? The other reasonable interpretation that you might have had is you might have said, okay, I just want this same bit pattern, but I want it to now be interpreted as a signed value. So I would want it to be something like this. So in order to get the negative 87, I basically have to just go ahead and manually redefine that right here. So that's what I'm doing. Let's just start from right here. All I'm doing is saying I want this bit pattern stored in memory. Okay, and this bit pattern is stored in memory, and this is a signed value. So now when I start doing the bit shifting, I have to do this sign extension of basically shifting in what the copy of the original most significant bit was. So that's what you can see here. This whole pattern starts moving down to the right each time. But what we start shifting in on the left is just basically a bunch of ones, right? Because that's the copy of the original most significant bit. And it does this to basically preserve this arithmetic reasonableness of basically dividing by 2 and rounding towards negative infinity with each shift, right? Okay, so that's what happens here. And lastly, what we'll do is let's go ahead and shift in a signed value again. So it's a signed SIGN, right? This is an int 8. And let's make the most significant bit a 0. So now it's the same thing where they get shifted, but now what we shift in or pad on the left is just a copy of all of those zeros. So again, it does that to maintain the reasonableness of the basically divide by 2 and round towards negative infinity behavior. Now, I know you're thinking this is a little bit esoteric, but I guarantee you this is going to come into play. In fact, in one of our next videos, we're going to look at interfacing with some sensors, and you're going to need this kind of information down the road. So anyway, I just wanted to be careful and complete in this discussion and show how the left and the right shifting happens. In this case in MATLAB, but it turns out this behavior is pretty much universal. So you go to C, C++, whatnot, and the left and the right shifting, and actually what we really should say is really it's the right shifting you have to be a little bit careful with, but it follows this kind of paradigm. Okay, so with that being said, I think we've got a good discussion now on some of these bitwise operations. Let's go back to the board and see what we can do with this now. All right, so now that we've got some of those shifting and other operations down, let's talk about generating some more complicated or more useful functions. So one of these first functions is something we're going to call a bit mask. All this function is in charge of doing is you tell it at what position do you want a 1, and it will compute the bit pattern that's needed to get there. All right. So this function is actually really simple. Again, all you do is you pass it in a position, and this is basically a 0-based index. So if you say position equals 0, that means I want a 1 to show up in this 0 position and then zeros everywhere else. Right? If you put in a position of 1, that means you want a 1 in the 1 position, etc., right? We're going to see later why this is called a bit mask, but again, this is all this thing is doing. It's really simple to do this, right? So the way you're going to do this is I'm going to go ahead and do something like this. I'm going to take the number 1, a decimal 1, and I'm going to then left shift by position number of slots. That's going to create some bit mask or some bit pattern. I'm just going to return that as the mask. So let's ask ourselves, why does this even work, right? Well, I think it's pretty easy. Well, let's go back and look at maybe this example, right? Let's go ahead and say position is 0, right? Okay. So the idea is I would want to get something like this coming out. Right? There's a 1 in the 0th position, okay? So let's check to see if this algorithm works correctly. So first of all, let's look at, okay, you gotta have a number 1. So here's a number 1, and again, we can write this down, okay? A number 1, what's the bit pattern for a decimal 1? Well, a 0, if this was all zeros, this would be the decimal 0. I don't want the decimal 0, I want the decimal 1, so that means there's just a single guy here, right? So here is the bit pattern associated with 1, with this thing right here. Now, all I'm gonna do is I'm gonna shift it over by position spots, right? So in this case, position is 0, so I'm not gonna shift this at all. It's just gonna be like this. And this is what I return, and that is exactly what I'm looking for right here, okay? Okay, that's pretty simple. Let's look at a more complicated situation. How about if this was like 4, right? So now what I want is I want a 1 to show up in the 0, 1, 2, 3, 4. I want it to look like this. This is what the function should compute, right? So again, let's just check the algorithm. It's really simple, right? So here's the 1, okay? And now I'm gonna shift this thing over by 4 items, right? So what that means is that, let me go ahead and erase some of these. So this 1 gets shifted over by 1, 2, 3, 4. So you end up with a 1 over here. Maybe I should have done this here as 1, 2, 3, 4, right? All this other stuff gets shifted. And since this is all left shift, I don't really care about the data type. All we're gonna do is pad on the right with a bunch of zeros, right? And again, we see this is exactly what we want, right? So this algorithm works. So bit mask is actually pretty simple to do. All right, so now let's use our bit mask function and build, and let's create a function that I'm gonna call bit set to 1. And what this does is, again, you pass this in a 0-based position, and also, I guess the first thing you tell it is a bit pattern or some value X. And what this function is supposed to do is it's supposed to go ahead and at this position, it will take that bit and it will just set that bit to 0, okay? So let's look at an example. So for example, if you've got some bit pattern that happens to look like this, so I've, 0B, 1101, 0101, this is actually the decimal value of 213. Okay, if this is an unsigned 8-bit integer, that's what this represents. And now if I say position 3, what that means is I want to go ahead and we want to look at position 0, 1, 2, 3, whoops. Oh yeah, sorry, yeah, right here. Yep, this one right here. Oh, sorry, I think I misspoke earlier. The whole idea is to set the bit at this position to 1, not 0. So you set this position right here to 1. So what you want coming out of this is you want 1101. This number here is going to change, and maybe I'll put this here as a different color. 1, and then 101. Okay, so what that actually is, I think this is the number 221. So this is what goes in. You give it 213 and 3 going in, and 221 should come out, right? That's all this function is supposed to do. So the way we're going to do this is, here's the algorithm. We're going to first create a mask at that position, and then we're going to take the bitwise OR of the mask with the original value. Let's see why this works. So again, here's our example, okay? Here's the 213. Let's go ahead and create a mask now at position, what was it, position 3. So what that means is we end up with, what here, 0, 1, 2, here, 3. So there's a mask here, there's a 1 here, and everywhere else there's zeros, okay? So that's what this mask is. Okay, so for giggles, I think if you're interested, this is a value of 8, but that really doesn't matter. Now, all we can do is we can take the bitwise OR of this row with this row. So again, just OR these two. So this, then this is a 1, this and this is 1, 0, 1, 1, 101, right? And this is actually a value of 221, which is exactly what we wanted. And as you can see, if you think about it and you stare at this long enough, what it's going to basically do is this is going to go ahead and it will basically make sure that this bit is set to 1, right? Because you can see, because the mask is always going to have a 1 here, so it doesn't matter what this number up here is. This could be a 1 or a 0. It will always be setting this to a 1. And everywhere else, it will just basically preserve the original value, right? So great, that is how to set this to a 1. What about if you want to set to a 0? Okay, so if we now want to create another function which now sets a certain bit to 0, this is sometimes also referred to as bit clear in some languages. And I guess I probably should have mentioned earlier, the previous function we looked at which we called bit set to 1. Sometimes that's just referred to as plain old bit set. So again, bit set means set it to 1, bit clear means set it to 0. I like to be a little bit more verbose just to make sure exactly what we're doing. So again, let's look at the exact same bit pattern. So you got this thing, 213, but I want to set now position 6 to 0. So that is 0, 1, 2, 3, 4, 5, 6. So this guy right here. So I want coming out of this thing a 1, and then I want this 6 value to be changed to a 0. And then you end up with the rest of this thing. What was it? 0, 1, 0, 1, 0, 1, right? This is what we want coming out at the end of the day. And again, I think this is actually a decimal value of 149. Okay, so here's the algorithm. The mask is the exact same. We just return something a little bit nuts, right? We return X and not mask. And again, let's go ahead and take a look through the example of why this works. So again, same thing, here's the 213, here's the X value, the original value. All we're interested in gunning for is, again, like we said, we're shooting for this. I want to turn this from a 1 to a 0, or if it was already a 0, just keep it as a 0, right? Okay, so a mask now, the mask is like we talked about earlier, it is now in position 6, so we're going to put a 1 here and zeros elsewhere, okay? Okay, and that one is actually a value of 64, but again, that doesn't really matter. Now, let's build this up a little by little. Let's take not mask. So this is just the not, so we just flip every one of the mask bits. So this is now 1, 1, 1, 1, 1, 1, right, like that. This is a value of 191, but again, that doesn't really matter. Now what we can do is we can do X and not mask. So what we need to actually do, we need to and the first row, right? Maybe we should indicate it like this and this. So we're going to and these two. So again, let's just walk down it. So 1 and 1 is a 1. 1 and 0 is a 0, right? 0 and 1 is 0, right? So all we're going to do is we're going to and the first and the third row. So 0, 1. Right? And we come out with 149, which I think is exactly what we were gunning for, right? Yeah, wait a second. Oops, what did I goof up? Sorry, I goofed up one. Did I goof up one of these? So yeah, I goofed up one right here. This one, I goofed this one up. A 0 and a 1 is actually a 0. Right? There we go. 1, yeah. Yep, there we go. There we go. That's better, right? So again, if you stare at this long enough, you'll see that this works even if this was a different value, right? So there you go. So here's how we can set a certain bit to 0. All right, so a very simple extension of this is actually, let's make a function called bit set to value. So you can now specify, do you want it to be set to a 1 or a 0? So we're just going to pass in a third argument, which is state. So if this is true, basically this means you want to set the bit at this position to 1. And then if it's false, you want to set this thing to a 0. Okay, so again, the easiest way to implement this is just go ahead and make an if statement. So if the state is true, use your bit set to 1 function. Otherwise, use the bit set to 0 function. So that's pretty kind of duh. The only reason I wanted to write this out is in the notes, I've got an example how people have figured out how to do this using kind of bit manipulations and bitwise operations. So I've got it here in the notes if you're terribly interested. It's using a couple of bits of logic where you kind of got to do some things, but it turns out it works. It's kind of fascinating, so check that out if you're interested. Otherwise, let's just use this really simple logic. Okay, so moving on, how about let's make a bit flip function. So here, all this is going to do now is you tell it where the position is, and I don't care what bit is in there. I just want to change it from what it is to the opposite bit. So again, let's look at an example here of the same thing, bit pattern we've been dealing with here. Let's use position 2. So that's 0, 1, 2. So it's right here. I just want to flip that value. So what comes out is I want this to be the exact same thing, except in that position, I want it to change from what it is to what it's not supposed to be, or the opposite, and then keep everything else the same. So again, I think this comes out to like 209 or something like that. Okay, so the way we're going to do this here, same thing, we're going to make ourselves a mask at that position, and then we're going to return X, and then basically exclusive ORed with the mask. So again, let's check out why this works. So the mask in this case is just a 1 here in this 2 position. Yep, like that. Okay, and zeros everywhere else. Okay. And what ends up happening here? This is I think this is 4, okay? As a decimal. Now all I got to do is exclusive OR these two. So okay, in this case, this is like a normal OR. So this is a what? We get a 1, 1. This is 0, 1, 0. Now here's the only place where the exclusive OR is interesting. I got a 1 and a 1. So the exclusive OR says this is actually a 0, okay? And then 0, 1, there we go. And I think if you care, this is 209. And you see, this gets us exactly what we want. So this ends up working quite nicely. Okay, so let's talk a little bit about making our function which checks if a bit is 1 or not. Now, unfortunately, I thought I hit record on my camera, but it turns out I didn't when I filmed this on the whiteboard. So I'm going to have to try to do a screen capture and just talk through the notes a little bit. And it's not that bad. This function is actually pretty simple. As you can see here, just like we've always done, you pass in a value. This can actually be a signed or unsigned value. It's not actually going to matter. Same thing, you give it a position, and here's what the algorithm is. You basically just go ahead and right shift the X value by this many positions. And again, this is why I mentioned earlier that this can be signed or unsigned. Like we talked about earlier, depending on the data type of this right shift is going to behave differently, right? It's going to behave differently on how the zeros or ones are padded in on the left, but it turns out it's not going to matter, right? Because you do this, you shift it, and then you do this. You return the value of the shifted value with a bitwise and 1, okay? And maybe what we're going to note right away here is when we say 1 here, this is simply the bit pattern of all zeros and a 1 at the least significant bit, right? Okay, so again, let's look at our example. So here's what the example looks like, same number we've always wanted to, and we want to check to see what position number 2 is. So that's 0, 1, 2. So it's this position. I'm checking to see if this is a 1 or not. So in this case, we can see that it is. So what we expect this algorithm up here to return is true. Okay, so let's talk about what that does, and let's see why that works. Let me pull up the example bits. And again, I apologize, we're just going to have to talk this through. Let me see if I can zoom this in. So again, here's the original bit pattern. We're checking if this blue bit right here in position 2 is 1 or not. We see that it is. So the first thing we're going to do is we are going to right shift this X value. So just take all of these bits and right shift it by, in this case, it's 2 positions. So you can see moved everything down 2. And again, here's where I'm just going to write XX. It's not going to matter if this is a 1 or a 0, right? So we don't care if it's an arithmetic shift or a logical shift. These are going to be some values. Who knows, right? And then we've got the 1 down here, which is just like we can see. It's this. And now what I want to do is I want to compare the bitwise AND of this row, of this row here and this row. So again, you compare, and then you can see this is why it doesn't matter if this is a 1 or a 0. It's always going to be a 0, right? Same thing here. Everything is always going to be a 0. The only place that this has any hope of not being a 0 is in position 0, right? And what we see happens is this bit that we were checking originally, it gets shifted into that position, in position 0. So this is only going to be true if the bit that we were originally examining was 1. If this was a 0, let me go for giggles. If this was a 0, it would have gotten shifted to 0 here. And then when we did the AND of this and this would turn out to be 0. So we see this all has the correct behavior, that it's going to return true only if this bit right here is a 1, and it will return false otherwise. So there you go. This is the bit to check if a bit is 1 or not. All right, so the last function we're going to make is, let's do the opposite. Let's check if a bit at a given position is 0 or not. So the easiest way to do this is just call the bit is 1 function that we just made, and then do a logical NOT. Right, so let's just make a quick note that this is a logical NOT operation. This is not a bitwise operation, right? So basically, all this is doing is, if bit is 1 returns true, then we're just going to return false instead, and vice versa, right? And the reason that I bring this point up here is that you might be tempted, okay, what if bit is 1? If this thing's set back true, right? We saw the way the bit pattern that comes out is 0, 0, 0, 0, 0, 0, 0, 1, right? Okay? If you did a bitwise NOT instead of a logical NOT, a bitwise NOT would flip all these bits. You would get 1, 1, 1, 1, 1, 1, 1, 0, right? And this is also true, right? Because this is not 0, right? So anyway, I think I'm getting everyone wrapped around the axle and maybe more confused than we need to be. Just make sure that this NOT operation is a logical NOT, not a bitwise NOT. Gosh, that's a lot of knots we're talking about. Anyway, maybe the easiest thing to do is to see all this in code. So let's jump over to the computer and look at an implementation of this in both C and MATLAB. Alright, so here we are. In the interest of completeness, I thought I would just show you that I've got pretty much all of these functions that we were just talking about implemented here in MATLAB, as well as some backing unit tests just to show how they work and how they operate. So you can run all of these if you're interested and see that they all pass. And I've got a link to the GitHub page where you can get all of these functions off of my MATLAB LUM repository. So I've got a dedicated video talking about how to get this repository downloaded, cloned, and kind of working with your MATLAB installation. So if you want to use my code that I've already got set up, feel free to check out that video on how to get them, or you can pull down these functions individually. And maybe the other thing that I will also point out is I also have this as a C implementation, so if you're interested, feel free to pull these down. I also have all of these functions implemented in C. I've got it here, and again, I also have associated backing unit tests so that you can run all these unit tests and make sure that they all operate as expected. And again, I have a separate repo for all of my C code, so again, if you want to check that out, I'm going to have links in the description of this video to both of these repositories so you can clone them and pull these down if you want these implementations. So, with that being said, I think this is probably a great spot to leave it. This is all the discussion I wanted to have on sort of doing bitwise manipulation. We're going to leverage this in a lot of our other videos where we deal with talking with sensors and specific registers, where we might have to get down to the bitwise level and deal with manipulating individual bits of variables. So that's probably a discussion for a later date. So like I said, why don't we stop today? I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Remember, the new videos come out every Monday, and I hope I'll catch you at a future discussion. So until then, I think I'm going to sign off. Talk to you later. Bye.